My name is Faseeh Ahmad, and I work as an AI consultant at System Verification. I would like to start by saying AI is everywhere, and we have seen what AI can do in the realm of softwares. Prime examples are chatbots or helpful assistants. But today, the topic of my webinar today is what happens when AI moves from controlling softwares to controlling physical machines. And you can call them cyber physical systems as well, like robots or autonomous vehicles, for instance. When AI starts controlling these cyber physical systems, small problems or small issues can actually become huge, can have huge physical consequences. And in such cases, um, reliability becomes a core issue. And that would be the core of what I would talk about in this webinar. So this webinar will be around 30 minutes, followed by 15 minutes of a QA session. And yeah, so let's begin. So agenda is very simple. So first I talk about, or like, let's say, give some applications of AI in these cyber physical systems or physical systems. Basically tell you what they're actually being used in, primarily everything. But later I will tell you about different kinds of failures, or like why failures are different when we have these cyber physical systems, which are being controlled by AI. And then why this makes it harder for QA, in the sense that, like, how can we quality assure such systems? Because now you have not only software, but also hardware in the mix that's being controlled by AI, and what kind of challenges essentially arise when that happens. Lastly, what I would try to do is I would try to talk about some engineering practices or some primitive solutions or things that we can do to make our life easier, or try to adapt QA into the mix, and we can design reliable robots using those techniques. So first, a short background. So I'm a robotics engineer and an AI researcher, and I finished my PhD in robotics and AI from Lund University last year in October. And during my PhD, I worked with self-reliant robots. So by self-reliant robots, I mean robots that can autonomously solve tasks. Additionally, they can adapt to some changes in the environment and, give solutions to those new, based on the new challenges. And lastly, they also have the ability to recover from failures. So you can think of them as embodied AI agents as well. And within this context, I have worked with skill learning, structured control, failure recovery. At the bottom of your screen on the right-hand side, you see a couple of robots that I have, worked with during my PhD. They by no means are the whole list of robots. There are many more, but the most common ones are like ABB Yumi, Universal Robots, KUKA, and then I also have some working experience with Spot Robot as well. After my PhD, I joined the system verification, and then since then I have been working on the AI validation and testing side. And currently I'm on assignment at Inca in Copenhagen and looking into robotics and AI together to solve tasks and problems for them. So why this talk? Or like in general, why are people here listening to me? The answer is pretty simple, and that is, now you see these AI-based robotic systems or cyber physical systems in industries, not only industries, but outside as well. Most common example is actually industrial automation, which I would say is the premier application of robots in industries. And these industrial robot arms are becoming more and more common in solving manufacturing tasks, specifically small batch manufacturing, where you have a lot of variability in tasks or different kinds of tasks that you need to solve. And these arms are pretty good at actually addressing those problems or helping humans in actually achieving the common goal. Then we move towards autonomous vehicles. Uh, I assume probably the most common example for this is the Waymo taxi. And if you have ever been to LA or San Francisco area, you might have seen these vehicles driving around, navigating on their own, and dropping passengers here and there from one location to other. Then you also have mobile robots. One common example is Amazon warehouse robots. Time and again, these robots have been quite fruitful in solving warehouse problems, taking stuff from one location to other location. Then we have a shift in these robots or the machines that I call them like the new modern machines or robots. This includes quadruped robots, similar to Spot Robot, and then the newest addition in the form of humanoid robots. I'm pretty sure you must have seen these humanoid robots somewhere online doing kung fu maneuvers, but pretty soon they will be pretty useful in or assisting your home environment or in industry environment, with a few caveats, of course. They still need some, more testing and durability. But having discussed these applications, the core issue remains the same. Previously, we were working with just software, so their consequences are mostly on the software side of things in general. But now when we have the cyber-physical system, especially robots, reliability becomes even more challenging because these robots or taxis or vehicles are working in an environment where they also interact with humans and also with other, critical things or materials or stuff. And in these cases, if reliability is not ensured, safety of human or even security of things can be endangered. And this is something I would like to, stress upon. And before that, let's try to understand what actually changes when you go from traditional automation towards AI-driven automation that we have right now or we're trying to achieve right now. So before AI, uh, you generally have a structure which essentially has three modules. First is inputs. These inputs can be in the form of sensors or whatever the user is actually providing based on task specifications. Then you have a controller. In most commonly used controller would be a PLC controller that would actually take these inputs and then basically decide based on some rules defined by the user and generate some control commands. Later on, these control commands are then used to control actuators that could be motors, valves, relays, conveyors, etc. You name it, you're basically doing it. And in most cases, you also have a feedback system, which basically tells what's happening, and then you can have a closed loop system. The beauty of this system is like it's deterministic and rule-based control flow, like you know what's going in exactly in most cases, what's happening, how you're deciding. And this predictable behavior has very interesting effect as well. So if any failure happens or any edge case happen, you can actually research that, analyze that, and actually devise strategy or like a clear validation process for that in the form of test scenarios or whatever you want to do. Super nice. But one drawback of this kind of architecture is limited flexibility, which means that you generally have to sit in a structured environment and you have a structured variables and some kind of things that you do. But like if you take the system outside, which I will talk about later on, then you will have problems. Now, when you have AI module in the system, what essentially changes is that like AI in this architecture operates like a brain. And instead of going into details of like how this is done, I would just say like it has like bazillions of different, units inside it. And the way it actually arrives at a decision is by adjusting the weights of these units, and you get probabilistic outputs. And then you also get non-deterministic behavior. Let's take them one by one. So you have input sensors that could be your traditional sensors in the form of camera, hearing, and then it goes into the AI module. AI module processes them and basically generates, in simplest words, based on the weights it has, it basically gives a guess, like this is the likely thing you should do. And that command is actually used for the planner, controller, or like the actual robot or whatever system you have. Then it has the non-deterministic effect. The simplest way to explain this is that I'm assuming everybody here is aware of ChatGPT or Claude Code or like similar like AI agents or AI modules. They might have used it that you have used. And if you try asking the same question to ChatGPT, it will actually give you different answers almost every time. That's something we call non-deterministic behavior, like you cannot determine what's going to be happening. So these two collectively are like one part of the problem, in my opinion, probabilistic outputs and non-deterministic outputs. The second problem actually is a byproduct of the usefulness of AI. So with the help of AI, what we have achieved now is that we can actually take our systems, that could be a robot or taxis, and actually put them outside in the outer world. This flexibility or this power has its complications as well. So when we were working in closed world environment, we had assumptions about or like cages around robots, assumptions about lighting of the system, what kind of inputs would go into the system, timing of those events, etc. But when you go outside, these assumptions do not hold because suddenly you encounter humans or you encounter a human which is basically running along with you. Then you have dynamic objects which are moving around you. So like the variables now are not easy to control. You cannot control them. And when this core assumption falls down, that's where your actual problem starts, because now we don't know what to expect. It's like an unknown territory for us. So then the question becomes like, how do we deal with this unknown or like unexpected situations, or prepare the system to deal with this? And this is a very hard problem. To dive a bit deeper, I will take some inspiration from the work that I have done during my PhD with the industrial manufacturing task or domain as the prime example. So on the top of your screen, you see peg in a hole task. So this task is actually a simplification of piston engine assembly problem, where we replace the piston and the engine assembly, where we need to insert the piston inside the engine with a peg in a hole, just to use it as a proof of concept. And here you can have a lot of things that can actually go wrong. For example, there can be a block that's actually blocking the hole, so you cannot insert the peg in the hole. Or when you try to grasp the peg or like a peg and you try to insert it in the hole, it actually drops off your hand. These are like small issues. And if your perception system do not detect these, you will have problems, because first, you will not be able to achieve the goal that you want reliably. Second, you can also endanger the environment that you're working in. So one thing I also need to mention, so these failures are not actually planning level failures, they're actually execution level failures. So what I mean here is that your strategy to solve a particular task does not have information on how to deal with these failures, because these failures only arise when you're actually executing the task. So for instance, misplacement of a tool, wrong grasp, or equipment damage, for instance. And when this happens, you have failures. And failures can be messy. They can have different forms, different shapes, and different results. So you have partial failures where you try to grasp the peg, you manage to do that, but since the grasp parameters were not correct, when you were trying to move the peg, it actually falls off your hand, and it can have cascading effects as well. So to understand that, So imagine that you have a task that you want to solve in 10 different steps. But like in step number 3, you actually encountered a problem which your system doesn't understand because the system never imagined this would be a problem. And the effects of those problems actually arise when you are at, let's say, step number 6 or step number 8. So, and those effects can actually carry on to the next parts of the solution or the problem that you're solving during the solving process. And one another issue that we have with these failures is like, since it's a very complex system, you have hardware as well and software as well. In almost all the cases, you're not very sure what the clear root cause is. So either you have, wrong parameters, is the peg too slippery, is the grasp force too small, is the hole misplaced, so like, is the lighting condition correct? So all these things matter, and they are actually part of why a failure happens. And it's not always easy to find out which one is the exact cause. And another aspect for this is like, since failure happens, they are inevitable. AI would fail, robots will fail as a result of it. But like, how do we address them? And one way to address them is to have some sort of recovery in the structure. And the most common way industry solve these problems is to have manual intervention, where a human being actually goes and understands the problem, and they're like, okay, we can probably try this and try to fix this. Another way to fix this is to use ad hoc fixes. You can understand it like fixing puncture wounds in your tire, for instance. So whenever you see a puncture, you basically put a tape on it, basically. And in generally, you don't have any system level strategies. Here, I will show you how system level strategies look like. So for instance, you pick up the block with the other arm and remove it. And if the block is too big to be picked up, you can push it with the other arm. Or lastly, if you drop the peg, you actually grasp it with the other arm and solve the problem. These are system level fixes. And one thing you will probably notice here is like, this is only true if you know such a failure will happen. So like, kind of like expected failures or known failures. And now I will show you why AI is super powerful and how we can use it in simplest terms to actually address unknown failures, or we can use them. Here, I will show you a video, which is basically test run on ABB Yumi robot. Here you see this control strategy, which is behavior tree, which basically, to understand it very simply, it tells how the robot should solve a problem in simplest terms. Then at the bottom, you see some text. This is essentially AI telling what if the failure has happened, what kind of failure it is, and how do we resolve this on the fly by fixing the control strategy. The task that we are trying to solve here is that we are trying to place same colored objects into same colored beans. And in this particular instant, the red object is acting as an obstacle because there is no colored bin like that. We start. So the AI understands and it devises a solution and fixes the strategy by removing the red object and then continuing the execution. Then in this case, we tried to push the blue, place the blue object inside the green because that was the goal. And while doing so, the robot actually failed because of unknown reasons, which is in this case, the human intervening. And AI understands that situation. And now what it will do is like, it will try to do the same action again to see if it succeeds or not. Then another thing with the same task, but now the red object is blocking the yellow one. So we automatically fix the control strategy or logic strategy and continue the execution. Here, something interesting happens. So the red object is blocking the hole in which the blue object is supposed to be placed, but we cannot pick the red object because the gripper affordance is not enough to actually pick it. Now the AI needs to understand this and also need to provide a solution on how we can remove this object. And in this case, what you will see is like, it tells you you need to do a push action. That's what it's doing. And then you do the normal execution. In this case, the goal is to place the blue object inside the green drawer. But when we try to do this, the drawer closes. So AI needs to understand the environment as well. And now it needs to open the drawer and actually continue the execution. Lastly, we see a very interesting case, which is when the drawer was closed, our system had no idea that the red object is inside the green in the green drawer. But when it opened, a new information pops up. So AI needs to understand like something changed in the environment and we need to adjust our solution accordingly. So what it will do is like it will remove the red object and then will place the blue object online without human intervention. So I hope this video actually shows you how powerful this is, but like at the same time, it also shows you that reliability is not something you can achieve directly. But even though like AI is controlling the system, there are so many things that can go wrong. Like maybe the sensor values that are provided to our AI system are wrong, and then it basically deduces a wrong solution and it actually implements it, similar to how an AI agent works. And AI agent usually works in software, but in the robot's case, this can be a very big problem. So I want to talk about something closely related to reliability and accuracy. So even if you have a model that's like 95% accurate, it doesn't mean that you have a reliable system overall. To understand that, I would like to give an example. So imagine that you have a model that you trained on with a certain data set, right? And when you test the model on a data set, you get, let's say, 95 or even 99% accuracy. Super nice. But that doesn't translate into a super reliable system. Reason is that 1% or 5% can have rare edge cases or hidden states in the system or environmental shifts, whatever, that are actually super impactful for the robot, because now you're dealing with physical environment, and let's assume that that 1% had cases where you are supposed to interact with the human itself. And if it's failing there, you can even end up hurting the human. And it's not that uncommon, I would say, that it has happened. And this results in compounded uncertainty that basically compounds over module to module, and then overall you lose the system reliability. So now talking about, I hope you have understood like what changes when we have AI in the system and effect of it on the physical systems or cyber physical systems. Let's talk about QA now. And to me, the biggest struggle for QA is the classical testing assumes determinism. To understand this, on the left-hand side, you have a software QA without AI, so without any AI, intervention. On the right-hand side, you have AI cyber physical systems, or like AI-controlled physical systems, together with the software as well. In general cases, when you have a software QA system without any AI, you have fixed inputs, reproducible bugs, or a clear validation process or clear specifications, something we talked about in the initial slides as well. But when you have AI in the mix, together with the problems of the physical system itself, you also have distribution shifts. You can have inputs that you know, but you also have inputs that you don't know about. For instance, autonomous taxis, there are so many inputs that you cannot process at the same time, and their effects on the environment. You just see the results when they have actually played their part. And this makes it very challenging because you cannot, address the problem prior. It's very hard in most cases. Then you have probabilistic outputs or non-repeatable outputs. Like outputs can actually change based on where you are, what kind of environment there is. Lastly, the implicit behavior that essentially comes from the non-deterministic inherent property of these AI systems that we actually use. And what are the consequences of these systems? There are lots of industrial consequences. First is, of course, downtime, like you have to stop the whole thing and investigate why this is happening. And this actually results in cost loss for the whole company, then you can also have safety related issues. You can expose humans or your environment in the surrounding to hazards or something or similar things. Lastly, maintenance complexity is another thing. So you have to, I mean, not only you are using these machines, you also need someone who is actually continuously maintaining them and trying to see, or like continuous software that's maintaining it and trying to see if they're running, properly or in a way you expecting them to. Now, before talking about what I have learned and the way I see how we can address these things in my limited experience or my experience throughout, I also want to address one another thing. So reliability problem is a common problem across different domains in robots, by the way, or cyber physical systems. So Waymo, like hearing about news about Waymo, I think I'm pretty much hear at least one news about Waymo where it's actually failing to get stuck in a traffic. Like last week or like 2 weeks back, I also watched a video where two Waymo taxis were trying to do a reverse maneuver and they were kind of stuck in a loop. So one tried to back down and the one moved forward and then the other moved forward and the other move tried to back down. So like it was a continuous loop. And then there were also articles about Waymo's, blocking the emergency, exits, which are usually used for ambulances or like police vehicles or, vehicles like that. Then you have example from Amazon itself, where like a lot of robots basically struggle to follow what the worker is actually trying to tell them, and all of them are actually like assembled together at a certain location where they were not supposed to be assembled in the first place. Then from humanoid domain, you see the Atlas robot actually struggling to actually maintain its balance and also placing things. You probably have seen a video of a robot falling off the stage as well, humanoid robot in the last in the last month or so. But like these things happen. And then drone crashes, I don't think so. I have to go into details. Like they are pretty common, even with such a sophisticated AI technology that we have, there are still crashes. So reliability is still a problem, and QA is something that is required in this context to achieve this kind of reliability. So what are my solutions? So my solution to this problem is to actually work towards reliability from day one. And how can you design a reliable system which has these AI-based components? The first thing we should do is or look into is like structure around your learned components. So what do I mean by that? So as mentioned before, like these AI components that you have right now, or the ones you use right now, I'm not talking about the classical, modules. Uh, they have so many, modules inside that basically decide on a certain, problem. It's very, very hard and even infeasible, I would say, to write unit tests for all the outputs for those internal AI, components. It's infeasible because they're like bazillions or trillions in numbers, actually. A better way to treat this problem, in my opinion, is to actually, instead of focusing on unit tests, you focus on behavior level tests. And behavior, what I mean is like, what is actually expected of the AI system? And that expectation essentially comes from those explicit assumptions that you make around the AI system. To simplify, basically what I'm trying to say is like you need to understand why you actually place a certain AI module in your system and what is expected out of it. And based on those expectations or requirements, you have to design behavior level tests or like abstract level tests around those AI modules. That's the first thing you should do. I mean, I would say is very important. Then runtime monitoring. This is something we have tested for years from our experience from software domains. Like there are countless research papers that support the idea of having runtime monitoring together with static checks, integration checks, and post checks and deployment checks. All these things they are still to be a part of your system. Another addition that I see when we have these cyber physical systems is built-in recovery. I cannot stress this enough that how important these things are. I actually wrote my own thesis about it, and recovery is a major part of it. How much recovery can save time when the robot or the system itself has the ability to recover from failures rather than relying on the human all the time, because it saves so much downtime and cost to the company if the systems actually have that ability. Of course, how to inject that recovery is not easy because, again, you have the challenge of reliability entangled with it. You have to be very sure how you build the recovery. And not all the systems require that recovery. It depends on the how critical your task is at hand. Lastly is system level testing. Instead of focusing on individual modules and testing them one by one, it is always a good idea to test the whole system altogether, possibly writing tests based on the requirements of the system as well. So based on these arguments that I provided, what should the companies do actually? Or like what kind of engineering practices should be done for AI-driven systems? And the reason I use the word engineering practices is because like when you're using an AI physical system, it's not like you train a system. You have to engineer that system because there are so many uncertainties that these AI systems cannot deal, especially when it comes to hardware. So at the end of the day, you have to act like an engineer as well. So first thing is system level validation from day one to day, end day, basically. Basically validating all the perception pipelines towards the actual implementation of those pipelines, like throughout. And I'm not saying this is an easy process, like engineering is not an easy thing to do, but to make this system safe and reliable, these principles need to be followed, and we cannot ignore them, especially in an age where we have these robots and taxis or like vehicles interacting directly with humans rather than behind the cages. Next important thing is uh, testing beyond the static test that you have. So this is very important. So uh, generally, when we train a model, we have some data sets and we train and we actually test them around these data sets and we draw a conclusion. Problem is, those data sets are never complete. Like you will almost always have a rare edge case, which can be very problematic, especially when you have robots or cyber physical systems involved. In those cases, what you have to think about, or what in my opinion, companies need to think about is like how to deal with an unexpected problem. And this actually boils down or comes back to my first argument, which is like your system itself should have some basic capabilities with AI, of course, in the mix to understand the problem and resolve it. And then you can actually train on those edge cases and basically have a growing system. Of course, there are limitations to it, and keeping reliability in check, of course, it would take so much time, but it's something nice to have, of course. Then we have the usual runtime monitoring behavior, and failure recovery strategies whenever possible are a must in my opinion. Like it's not something of an afterthought. It needs to be from day one. Like you need to look at it from QA perspective from day one, like what can go wrong, what doesn't go wrong, how it can go wrong, and all those things. And it's not easy. I'm not claiming it's easy. And lastly, validation is not something you do once when you have the system. It's a continuous process. It basically means you have to keep maintaining it. You cannot basically slack off. With that, I would go towards my last slide, which is how I personally view the future of this physical AI. I personally do not see degradation of when it comes to the usage of these tools. I think of future of physical systems in the form of hybrid control architectures where you have your traditional units, which are designated for task, but then you have this AI core as functioning as a brain, if you may, if you want to think, that's responsible for learning, adaptation, understanding the problem, and all those things. But you cannot leave this AI core on its own. You need to have a safety layer, sort of a safety layer, that validates, that monitors, and possibly installs guardrails around what the AI is supposed to do, and what it's not supposed to do. And with this continuous validation, failure recovery, and that the system can do, you can end up with responsible AI that can help you move, that can help you in achieving your goals or task at a much safer and a very fast pace. Lastly, I would like to thank you guys for listening. And I would end with this quote, which is when AI controls machines, a small uncertainty becomes physical reality. And thank you for listening. I'm open to questions now.
You can write questions in the chat or in the FNS or Q&A section.
I have a question, Faseeh, and thank you for the good presentation.
Yes.
Regarding the future and reliability of those different kind of robots, do you think we would have them as enough reliable to actually have them more for people to have them in their home doing classical task, for example? Or how close are we to, because then I think you need a quite high level of reliability and confidence if,
Yes.
not how to say it. What is your view of the future of the robot in the homes, basically?
Yes. So I'm actually an optimistic person
Mhm.
when it comes to applications of robots together with AI and also with QA. And I would say we can definitely see a future where we have these robots working as home assistants, like doing laundry for us. Like there's actually a startup from San Francisco, Physical Intelligence, who are trying to solve these tasks. And I don't know, cooking for you. But of course, it has some caveats that we are still facing. First and foremost, in my opinion, like they're using humanoids, like a lot of these companies. Humanoids, even though are very useful, but they have a very big problem right now, which is in the form of dexterity. It's a physical issue, like the humanoids itself are not capable enough, in my opinion. And there is also a report by, I forgot the name, where they were talking about the lack of dexterity and how they cannot do these tasks the way a human can do. But I would also like to say, like, there are companies which are actually working on this side, and I see like a future where we will develop these humanoids which are capable of solving these things. And when this happens, we can combine them with this safe, reliable AI system, which we are very far off from now, I would say, because right now our focus is to use this AI to do the task without caring about the consequences of them. We can see a future, let's say 10, 15 years, maybe, uh, we will have robots at home for sure.
Hmm.
Like we are already seeing robots outside digging up snow, actually clearing paths. They're already there, but proper functional one, I think at a more higher scale, it's just going to increase now again more than before, I would say.
Yeah. Thank you. I like your optimism.
Yes. There's some chat, I think. Yeah, please feel free to answer. No question is off limits here. Just whatever your thoughts are, if you think you want to talk about the future, how I feel like it would be, just go ahead. Oh, we have a question. Nice. Yeah, I have a question from, so I have a question about AI reliability. Are there some benchmarks, metrics to determine how much reliable these systems need to be for them to be used in particular scenario? Short answer, no. Even if there are some benchmarks, I think you can find them on Hugging Face. The problem with those benchmarks, in my personal opinion, is that they are not complete enough. And the reason I say they are not complete enough is like you can probably design a scenario like a structured one and use those benchmarks for that one. But like as soon as you invalid some of the assumptions about the scenario and avoid those assumptions, you end up in a situation where you have a case where those assumptions don't hold. And then those benchmarks that you train the model on do not have that information because it's actually a very interesting question. I would like to elaborate a bit more. So the AI models that we use right now, they don't reason like how humans do. They're essentially pattern matching, doing pattern matching. So they look at whatever data you provide them, and based on that, they look, oh, this is the most closest solution to this problem. Of course, the space itself is not possible to imagine. And then they pick the most closest solution. So it's not like reasoning. So that's why when something is not inside the benchmark, uh, you cannot trust the AI to be reliable. Like there is no metric that actually tells you it's reliable. I hope that answers the question. Uh, oh, nice. Yes, another question. Thank you for the great question. Yeah, how extreme could things get in the future when we eventually have fully autonomous AI cars? How safe will they really be? That's a very good question. And I think a very hard one to answer as well. Um, and I'm just trying to think which perspective I should take to answer this question. Because there is a perspective where if we get level 5 autonomous vehicles, when I say level 5 autonomous vehicles, I mean vehicles that need no human intervention at all to drive, basically. You have vehicles like taxis, for instance, which are level 4 right now, but like the publicly driven, like the privately owned vehicles, there are only 2 or 3 vehicles that are level 3 autonomous. And the autonomous taxis that we have right now, they are very structured in the sense that you have limited area where they can drive. So for instance, in LA or in San Francisco, but you don't have them, let's say, in, I don't know, in the state of Colorado or other states. So they have to do a lot of, around, things around it. But coming back to your question about the future, um, it's not that easy because like if we have a fully autonomous driven vehicle, um, I would expect them to be really safe. In a way, I would personally expect them to be safe because if vehicles itself are, driving with the help of AI, but you need a system as a whole that's also, monitoring how the vehicles are being driven. So maybe there's some information going on from one vehicle to other. I would expect this to be safe. But realistically, having such a system where you're knowledge sharing at this scale, it's not that easy because it requires so much data transfer in small amounts of time. Like probably in very far future, yes, then we can assume we will have more and more reliable system. But in near future, like just having fully autonomous vehicles, I don't think they will be super reliable, at least initially. That's my hope. That's my perspective. So for instance, you probably have looked at articles which talk about Tesla actually causing an accident. There are lots of them, by the way. Like still, like these vehicles have a lot of accidents going on, and achieving level 5 autonomy doesn't mean they will automatically achieve a reliable AI. If that answers your question, there's still a lot of things needs to be done. My point is like it's a separate problem, like achieving level 5 autonomy and making sure that autonomy is reliable enough. to be driven by AI is a separate question. And I think the second part is even harder than the first one. Hope that answers your question. Okay.
If there is no other questions, maybe that's it for today, Faseeh.
I think I see someone writing in the chat. Maybe we can take that.
Absolutely.
Okay. It seems like a pretty long message. Okay. Okay. I mean, I think it's probably taking some time. Maybe we can take questions afterwards as well. I mean, how should we do this, Miriam?
If there is any questions, they can send them in when we send out the recording. So they can just respond to that email,
Yes.
and that will be coming at the latest tomorrow. And if there's any other questions, you can also reach out to Faseeh on LinkedIn, right?
Yes.
And I can also add his email. So if there's anything else you want to discuss with him or ask him, he will be available for answering your questions.
Yes. Yeah, with that, I think thank you for joining again. And should I close the session now?
Yeah, we can wait. But thank you everyone for joining, and
yes.
Hopefully you learned something new.
Yes. Thank you.